Hi, in this video, we're going to take a look at full factorial experimental designs. Okay, so in experimental design, this is our game plan for collecting data before we actually collect data and look at data. And so our goal whenever we do design of experiments is to set it up so that after I get my measurements, after I get my data, after I get my observations, I have the best data I could possibly hope for. And we want to set this up so that we have as little data collection as possible. We want to get the most bang for our buck, and we want to do as little work as possible. And so what we're going to do, we're going to do prior planning to get good, solid data. All right, so in factorial designs, what we're going to do, we're going to focus on two levels for each of our predictor variables that we're interested in. And so if I have categorical data, something like male, female, if we were to have, left side, right side, up, down, on, off, anything like that, that's very natural. Now, if I have a numeric variable, what we can do, we can pick in our experimental design, we can pick extreme values, like a very, very high value and a very, very low value, high but reasonable for what's going on, and low but reasonable. And that way we can set up so that we got two levels going on and we can proceed. All right, so now what we're going to do is in full factorial experimental designs, for all of our predictor variables, we're going to set up our experiment to get every single combination that we could have. All right, so we're going to have powers of 2 on this. So if I have only one variable, power of 2 to the power of 1 is just 2. If I'm going to have two variables, I'm going to have 2 times 2 to the power of 2 is 4. If I'm going to have 3 variables, then I have 2 times 2 times 2 possible combinations. That's 8. 2 to the power of 3 is 8. If I'm going to have 4 variables, that's going to be 16. 5, 32, and then 6 is 64, then 128, 256. And you can see that these numbers are growing very, very quickly. So typically when we have a lot of predictor variables, we don't do full factorial experiments. What we're going to do, we're going to look at fractional factorial experiments in an upcoming video. But right now, we're going to take the point of view that we have enough time, money, and resources to execute a full factorial experiment. We can get all possible combinations of our two-level variables. Now, something that reinforces this idea, when we have two levels of a numeric variable and I make them very far apart, that's going to maximize the variance of what I observe for the predictor variables, and maximizing the variance decreases the standard error of a regression coefficient. And so this will even reinforce this aspect of getting good information in there. All right, so let's go ahead and dig into this. All right, so first thing I want to do, I want to look at basically a bad design first and foremost. Then we're going to improve it. Then we're going to make it even better. All right, so let's take a look at this. If this was my design, remember that when we do design of experiments, I have not looked at my response variable. I have not looked at my dependent variable at all. And so to emphasize that, you notice I have question marks. These question marks are standing for the data I'm going to collect. What we're going to do is that we're going to set up that here are the values for the predictor variable, and then I'm going to look at the dependent variable, and that's how it's going to work out. And I'm going to go through and collect data this way. Now, look at what I've got. I've got male. Every time we have male, we have left. And every time we have male, we have left. And we have high. So every single time, we have the same thing over and over and over for these 4 rows of data. And here I've got female, right, and low. So if I was to go out and collect the data, since there's this perfect matching aspect, I want to know, is it sex? Is it side? Is it treatment? Is it a combination of them that's leading to the result I observe in my response variable. And so this is a poorly designed experiment. Well, can we do better? Yes, of course we can do better. So let's go do better. All right, so here I'm just going to improve it a little bit, not perfectly, but this is improved. So now notice I've got sex goes male, female, male, female, male, female, but side and treatment, I still have that matching aspect. Every time it's left, I see high on treatment. Every time the side is right, I see low for treatment. All right, and so this is improved, this is better, but on this one, if side or treatment is statistically significant, I don't know, is it side? Is it treatment? Is it a combination of the two? I have no way of figuring that out. Now, I can figure out something about sex, and I can figure out it looks like something is going on with side and or treatment. So there is informative value, but I really don't have enough going on here. So notice how I shuffled the male-female across all the values of side and treatment. So let's do this one more time. And to do this, I'm going to use the expand.grid function. And so this is the easiest way to generate these that I've found in base R. There are packages in R that will do this for you, but I like doing it with expand.grid when I have relatively few predictor variables and relatively few levels of those predictor variables. And so here you'll notice I alternate male, female, then I go left, left, right, right, left, left, right, right. So, here each level appears once before switching. Each level appears twice before switching. And here each level appears 4 times before switching. And you'll notice that all possible combinations of sex, side, and treatment are in there. And so with this experimental design, we're going to end up getting like all the possible combinations in here. And this is going to, I've exhausted all of the different possibilities. All right, so this is a good experimental design. Now, something that is a huge drawback of full factorial experimental designs is that it takes a lot of data. Here we only have 8 because I only have 3, but very quickly, if I was to have more, predictor variables, or if I was to have more than 2 levels in predictor variables, the number of distinct combinations I can get grows really, really quickly. And in that case, it's typically not even going to be feasible to do an experiment to address all the variables of interest. All right, so now let's go ahead and consider interaction effects. So here, what I want to do, I want to just go through and just manually show like what is the interaction representing off of this. And so this really is not a very informative, but here I put on an intercept because we're going to be doing a linear regression model with this. I have my main effects. Here I have my 2-way interactions. I have my 3-way interactions, and then I have my dependent variable. All right, so this just kind of shows what each column of interaction is representing. But you know what? Let's do this a different way. Let's set this up so that instead, I'm going to represent each of my main effects with plus or minus 1. Okay. And then for my interactions, I'm going to multiply the main effects. All right, so if I want sex inside, I'm going to multiply the sex inside columns. If I want the sex and treatment interaction, I multiply the sex and treatment columns. If I want side and treatment interaction, I multiply side and treatment. And if I want all 3 interaction, then I multiply all 3. Okay, so now we can see that we've got everything worked out as plus or minus 1s. Now, the first thing I want you to notice as you look through, if I was to go through and add these all up, add up each column with the plus and minus 1, you'll notice that all of them add up to 0. All right, well, it works out that, if I was to take the intercepts and each of the plus or minus columns, they're going to have 0 correlation with each other. They'll have zero covariance. Okay. Well, I'll go a step further with that. If I take any two distinct columns, they're going to have zero covariance between them. And as long as it's not the intercept, they'll have zero correlation. The intercept has zero correlation, so zero variance. So the computation of correlation doesn't make sense, but covariance will be zero. And now let's go a little bit deeper. How many rows do I have? 1, 2, 3, 4, 5, 6, 7, 8. How many columns do I have? 1, 2, 3, 4, 5, 6, 7, 8. All right, so I have an 8 by 8 matrix where the correlation is zero between the columns, or covariance, if we're talking about intercept. Well, that zero covariance in statistics, a covariance of zero corresponds to orthogonal vectors. We have orthogonal columns from linear algebra. So I have an orthogonal matrix, and it's and it's square. And so what this is setting us up for is that this is the most informative type of matrix that I could get off of 8 rows of data. And so this is very powerful. I have the ability off of 8 observations to get the intercepts, the main effects, the two-way interactions, and the three-way interactions. And this is the least amount of data to be able to achieve all of this information possible. Also, when we have orthogonal columns, we interpret the columns as having like completely distinct information. And what this does for us is this makes it easier to interpret our regression model coefficients. So imagine if I have a human being and I was to take their height and I was going to take their shoe size. All right, height and shoe size are correlated. So if I had height and shoe size as a predictor variable, since they're correlated, they're bumping up against each other. And so it's harder to interpret a direct relationship off that coefficient because there's kind of a balancing act in my data. It takes a lot of data to really pull them apart. But here, when I have zero correlation, zero covariance between our columns, this sets it up so that each coefficient is completely separate from each other, and I have completely independent interpretations. Now, if I take the covariance of my design matrix, you'll notice that what's going to end up happening is I have zero covariance between distinct columns, and then the covariance is going to be a constant for each of the individual columns. If I take the correlation instead of covariance, what's going to happen is that on the diagonals, I'll have 1 for the non-intercept columns. I'll have 0 on the intercept because after I subtract the mean for the covariance, I'm just going to have the 0 vector, so that's going to be 0. And then because of the inability to compute correlation with a constant vector, the correlation will be equal to NA. If instead I did correlation instead of covariance. Also, you'll notice that the determinant of my matrix is not equal to 0. First of all, it's computable. The determinant is computable because I have a square matrix. So we also have more linear algebra tools going on than we have with a regular setup. So this is, think of this as the most information I can possibly get out of such a small collection of data. Now, we've got main effects and interaction effects, and we're setting it up so that they're linearly independent of each other. They're orthogonal vectors, and so this makes it easier to interpret what's going on. Now, a huge drawback about this in this full factorial experimental design is that when I have a lot of predictor variables, the number of distinct combinations gets really big, really fast. And it might not be possible for us to collect that much data. I may not have the time, I may not have the money, I may not have the resources. Maybe my boss doesn't have the patience for it. And so what we're going to talk about in a future video is fractional factorial designs, where what we're going to do, we're going to select a fraction of the rows to work with, and we're going to end up using a little bit of abstract algebra to really get as much power out of the incomplete aspect of the data as possible. And here are some homework problems for you. It basically just, go through, generate a situation, and do some computations. That's that. All right. Well, that's all I've got for you. Life is short. Do math.